Yeah, we have discussed all these types of particles, types of decays. Yeah, the area what we were going to discuss today, that was the types of decays. What we are going to discuss, the types of decays, right? That is basically the part, the phase of particle physics. And in that one, when we are at the types of decays mean when the radiations are emitting out, there are two types of decays actually. One is alpha decay, one is beta decay, and one is gamma decay. But beta decays are of two types: positive beta decay and negative beta decay, right? Alpha decay is that one in which alpha particles are emitted out. Got it? What happens when alpha particles emitted out? Beta decay is that decay in which an electron or a negative beta particle emits out. Positive beta decay is the decay in which a positron or a positive beta emits out from the nucleus. So we will have a discussion, detailed discussion about those. Gamma radiation, when energy level decreases, because during gamma nothing happens. Okay, now come to that point. That is, for example, in this table, this would be, this is a detailed discussion about three types of, radiations, their traits, and their profile picture. So the properties are there, then and types of types of particles are there. I believe that this is very common and very easy to remember for, and you are aware of this all. Nothing
Yes.
detailed in that one. So there are alpha particle, beta particle, gamma particle. Their charges are given, relative masses are given, their nature is given, right? And then their symbols are given. So everything is discussed. And we have discussed everything. Then this is a table in which we have to discuss about their properties, right? That what is their speed and what else. This is actually the continuation that of the same table, but this is 5, 6, 7, and so on. So here the properties energy, it has a discrete energy level. Discrete energy level mean some specific amount of energy. Beta particles have variable energy range because of its kinetic energy, because of its velocities emitting out from different nuclei. Then gamma radiations have discrete energy level, which is basically equals to E is equals to HF. We will discuss in the quantum. Then speeds are almost 0.05 c, yani 5% of the speed of light. Then it is almost 99% of the speed of light, beta particles, and alpha gamma particles are exactly move with the speed of light. Ionization power levels are given, but you can simply say that ionization power of the alpha particle is highest, then beta, and then gamma, and penetration is lowest for alpha and highest for gamma. And then they can be blocked by the paper deflection. We have discussed everything. This we have discussed the deflection of alpha particles and beta particles. Here there is an important thing, that beta particles have a lot of paths, right? One is the thick one. Do you know why do we have that thick path? The thick path is actually due to average, because beta particles have lot of you know ranges are in fact lot of reflections because of its speeds, different speeds, so they have deflections. So we just say that gamma particles have no deflection and beta has a lot of deflection, but we take an average speed of that, average deflection. And then uh, yeah, I have discussed everything over here, that why don't we have the single path, reason of that. And yes, this all is clear to you. This is the topic what we had to discuss today. And then from here I will move to the particle physics. Decay, nuclear decay means when a radioactive parent nuclei is disintegrated into a daughter nuclei and it emits some particles. So that is called its decay. What do we call it? It is a decay. So decays are having a lot of equations. Like when alpha particle would be emitted out, it is called alpha decay. When beta particle is emitted out, it is called beta decay. and so on. So every decay has a specific property, but generally there is a situation what we have to discuss. That situation is that if we are having or if we are going to represent a nuclear decay equation, that equation should have some nuclide notations, and those nuclide notation must have nuclei number, nucleon number, proton number, z, and it's yeah, these two should be the nucleide notation. Then there are some important parameters which you must know, that during a decay, nucleon number, proton number, energy, mass, momentum, they all are conserved. It's very important, right? They all are conserved in the nuclear reaction or any process, right? So number of neutrons, they may be not conserved, because when we say that I will talk about beta decays. In beta decays, the neutrons are changed. In both the beta decays, neutrons are changed. So that can be that can be a sort of discussion in which we can say that neutrons numbers are not change, are not same, but rest all parameters would remain unchanged. Yani they would be conserved. Simply I will say that they will be conserved. Is it clear to you? Conservation means, do you understand conservation?
Yes.
Okay, so here we say that when alpha decay takes place, what happens to the parent nuclei and what are the traits of the daughter nuclei? In an alpha decay, actually, your Z is decreased by 2 and your A is decreased by 4. Do you know that? Yes, yeah, yeah.
Yes.
H, I mean, alpha particle has a property that its Z is 2, A is 4. So when this would be emitted
Yes.
out, this is emitted out, then the parent
Nuclei.
nuclei would have a change.
Yeah.
And
Yes.
general reaction is that Z is decreased by 2 and A is decreased by 4. So for example, if uranium undergoes an alpha decay, what would happen? It is converted into thorium by emitting an alpha particle. So what would happen to uranium? Uranium 92 238 is actually the main yani parent nuclei, and that parent nuclei is converted into daughter nuclei to He4, and thorium is 90 and 234. Is it clear? It's very simple.
Yes. Clear.
ठीक है ना? And when we move on to the next, that is, yeah, this is sometimes this type of question is asked to you, that during an alpha decay, what would be the change in position of nucleon number and proton number in in the grid? So in the grid, actually, if you see that A is decreased by 4, so on y-axis there is A and on x-axis there is Z, so that will be decreased by 2. So in diagonally, the element would yani the position would move towards left down. Got it? Towards left down. So if it is Z, Z will be decreased by -2, so it will reach to this position, Z minus 2, and A is 4, so it would become A minus 4. So that will be basically it's A minus 4. Is it clear?
Yes. Clear.
Thank you. Okay, the next is your beta decay. Beta decays are of two types. One is your negative beta decay, and the second one is your positive beta decay. Actually, negative beta decay takes place when a neutron is converted into a proton and the excessive mass is released in the form of released in the form of negative beta particle. ठीक है? Is it clear to you?
Yes, clear.
Okay, so yani simply we can say that a nuclear decay, yani a beta decay. Do you hear me?
Neut- yes, just
When I will
one.
be at mute, then let me know because my mic is
Okay.
working for last 2 hours, so maybe it would
Oh,
discharge.
okay. Just one question
Okay.
about this neutrino.
Uh, uh, Sorry, do you have a
What's this,
question?
what's this neutrino exactly?
Oh, yes, I will talk about that. Actually, every particle has an antiparticle. Yani every mass has a anti-mass, or yes, you can say, but every particle has a antiparticle. So the antiparticle of that negative beta decay, yeah, negative beta particle, yani electron, is your antineutrino. Okay?
Wait, negative beta?
Yeah, negative beta mean electron. Na? Just see it.
Yes.
This one.
Oh,
This is an
yes.
electron, right? So this is your electron neutrino. Electron neutrino mean it is basically an antiparticle of an electron. Okay? So
Isn't it positron?
no. Positron is basically a positive beta decay.
Uh,
Okay? Positron is an antiparticle of electron, you can say, but during this, to balance the mass and charge and kinetic energy, a particle is emitted out, which is basically very unstable particle. It is, I will talk about that. That is lepton. What is that particle? It
I
is
don't
from
know.
the lepton family because we have not yet discussed. That's why I'm not going to drag you there. But when I will go back to the particles, subatomic particles, I will discuss that in detail. Okay.
Okay.
Okay. The main identification of that is during this, a neutron is decayed into a neutron is converted into a proton, and an electron antineutrino is generated. Check this one out. During this, Z is increased by 1 and A remains unchanged. Got it? Are you getting it?
Yes. I
Okay.
guess.
So during this all, if I just see on the grid, what will happen? As A remains unchanged, so y-axis will have no change at all. Is it?
Yes.
And there will be a change on x-axis, and that change is what? That change is your yani Z is increased by 1. So when Z is increased by 1, there will be a right shift, yani right shift of 1 in your, in what? In your Z, yani in your proton number. Are you getting it?
Yes.
Yani here, just see that if it is Z, it is Z plus 1. Na? So if it is A, this is again A. There is no change at all. Clear?
Yes.
Okay. Go back to that. There are some important specs about that. Negative beta decay, proton. Okay, this is clear. Then this particle, about this particle, that another particle called antineutrino, it has no mass, no charge. And when it has no mass, no charge, then what? It has negligible mass. It is also emitted in from the nucleus at the same time. Here a neutron Yes, this is the main point where I wanted to bring you. Here, a neutron is changed into a proton. Yes, this is very important equation, that a neutron is converted to a proton, and additionally a beta, negative beta particle, this one, and an anti neutrino. Anti neutrino has a sign 0 0 and -1 at the bar, that is generated. Got it? This reaction is asked to us, yani in different situations. Okay. The next is positive beta decay. Positive beta decay is basically a positron or a positive electron, you can say. And when this decay takes place, your positive electron, your positron, is emitted out along with a neutrino. This is neutrino, right? What do we call it? Neutrino. The if it had a bar, it will be called antineutrino. Okay, is it clear to you?
Yes. Okay.
Okay, so simply, actually, this all is to remember somehow. This is sort of information till this point. During this, Z is decreased by 1. A remains unchanged. So if we say that then when Z is decreased by 1, check this one out. That if your element was at Z, Z was here, and then this new position is Z minus 1, isn't it? This new position is Z minus 1. So when it is Z minus 1, I can say that its Z is decreased by 1, but A remained unchanged, so it moves diagonally towards, sorry, it moves horizontally towards left. Come to that point, point 2 and point 3, they are equally important. Point 2 is clear that there is an there is a neutrino with negligible mass and no charge. It is also coming out of the nucleus just to make the equilibrium. That's it. Nothing, there is no other reason behind that. The main equation is that the proton in the nucleus that changes to a neutron, a positive electron and an antineutrino are released during this all. So this is the equation you have to remember, right? In these type of questions are asked, that you would have nothing to be written here, like there would be empty spaces, blank spaces, and you have to fill them out. Is it clear to you?
Yes.
Ab dekho, this is the million worth, the reason of beta decays. Beta decays are electron and positrons are due to weak interaction. Yani, there are two types of nuclear forces or nuclear interactions actually. We define them. One are called strong nuclear forces, due to which the protons and neutrons and quarks are formed and deformed. But there is another one in which we can say that there are the weak nuclear forces, right? And in the weak nuclear forces, the range of these nuclear forces is within the nucleus, right? And yani, we can simply say that if if we consider that these all forces are inside the nucleus, then it is definitely they are called short range forces as well, but they are weak short range forces. Okay.
Okay.
Okay, then let's talk about gamma radiations, gamma decay. Gamma decay is nothing, just the energy level changes, just energy level changes, and when energy level changes, the A and Z remains unchanged. Just check this one out. If you have thorium 90 and 34, then what will happen? If there is a gamma decay taking place, it will remain 90 and to 34, but a gamma will release, but the energy level of thorium is less. Are you getting?
Yes.
Okay. This is basically a sort of note about this and then a summary that if we say that the parent nuclei is unstable and excited to form a stable nuclei by emitting a gamma particle or a gamma ray, and in gamma emission no particles are emitted, there are only the change in, that's why there is only the change in energy level or energy state, but particle number yani mass number and neutron number that remains unchanged. Okay,
Okay.
this is the summary. Just have a quick eye view, bird eye view basically, and tell me, is there anything what is new for you or which is not known to you? No.
Oh,
Is it all clear?
yes, but just one question about this neutrino again.
Mm-hmm.
What's like the difference between neutrino and antineutrino? Because, for example, in electron and positron, charge is different. What is different in these?
Yes.
Like both of them are neutral.
Yeah, both of them are neutral, but when mm, in the nuclear reaction, actually they all are just the yani nuclear yani energy balancing particles. You can simply say that these are some sort of uh, yani those particles which are emitted to balance the reaction. Okay? just just
Uh,
that is one reason behind that they have to yani they are generated to balance the reaction.
okay.
Got it? I will
Yes.
maybe I will be able to explain you in detail, but I think so it would be beyond that, and I will try my best to discuss that in another class for neutrinos and antineutrinos, because there is a summary of the particles na? Yeah, this one. Okay, just a second. This one, the part 2.
Okay.
Okay, check this one out.
Quarks up, down.
Yeah.
No.
So this is basically a sort of discussion we have to make. Got it?
Yes.
Here. Okay. Just a second. Where was I? I was at this point. This is very, very important topic. That is, let me just re-record that.